Hi, everybody. I'm Professor Kendra Irk, and I'm Associate Professor in Materials Engineering at Purdue University. My research is broadly focused on studying the mechanical and flow behavior of soft materials and complex fluids. For instance, we study the flow of concentrated suspensions, such as those formed from biomass, ultimately to make ethanol and other renewable fuels. We study the microstructure of surfactant pastes that are used in detergents and personal care items, such as shampoo and conditioner. We study the stability of oil and water emulsions so that we can figure out better ways to keep these from being generated by industry or by ships, for example, and keep them out of the environment. And we study the swelling and transport behavior of superabsorbent polymer particles, actually for application in concrete, which I'll tell you about here. So one of our biggest research projects is looking at the application of hydrogels as internal curing agents within concrete. The hydrogels start out as dry particles that swell with water, and then they release the water as the cement cures, ultimately forming a stronger, more durable, and denser cement matrix, and resulting in concrete that has higher strength and longer service life. Our lab specifically makes unique hydrogel formulations that include things such as nanoparticles to catalyze the cement reaction and other unique additives to control the water transport to and from the hydrogel and the cement matrix. My group also focuses on unique laboratory capabilities to link the structure of a material with its rheology or with its flow behavior. So for instance, we have a few different rheometers in our lab that are equipped with ultrasound transducers and lasers and high-speed cameras to allow us to visualize and image the materials as they are deformed and shear within the rheometer. So for instance, you see here a viscosity versus shear rate curve of a concentrated surfactant paste. We can actually do local velocity measurements at every point in time. And I can tell you exactly that shear thinning viscosity behavior is due to the fact that the surfactant paste, when it's in its lamellar structure, is actually undergoing both wall slip and shear banding as we're deforming it in shear. That's not something a normal rheometer can do. We customized ours to be able to link the rheometry directly to the flow visualization and ultimately see how the flow behavior changes the structure of our materials. My group is always very diverse in terms of academic backgrounds. We welcome folks from all the engineering disciplines, as well as pure science and math disciplines. Ultimately, my research is materials engineering, so it pulls together a lot of different typical majors and disciplines. So the more diverse my group is, the better we all perform as a team and the more we learn together. So I'm interested in working with people who are curious and enthusiastic about materials research, willing to learn some chemistry, apply some physics, do a little bit of math and coding. Ultimately, at the end of the day, we're all big nerds about soft materials. So I encourage you to email me, go to my website if you have more questions or interest in learning more about my research at Purdue, and best wishes in your graduate pursuits in the future. Boiler up.